Welcome back to the blog on fluid dynamics. So again, we have two speakers. First one is Christoph Lehrenfelds. Christoph joined the club in 2007, 2008 as a baby student in the fourth semester or so. Already this time he started with hybrid DG methods, and it was a new drive with NGSolve this time, connected with RWTH Aachen. I think he's very well known for this HDIF conforming HDG, hybrid DG. But besides this, he is not only doing DG in West-Oaks, he is developing a big CutFem add-on package on top of NGSolve, which we will see in the afternoon.
No, tomorrow. Yeah.
Tomorrow. Okay, shocking. Not trying to shock you. Okay, so Christoph came with his big gang from Göttingen, and always happy to have him in Vienna. Yeah.
Okay.
Nothing more. So, please.
Okay. Yeah. Okay. Yeah. Thank you, Joachim. It's always great to be here. Okay. Yeah. So actually, when I think about this, so I mean, this is essentially what we started with 16 years ago. I guess when Joachim was in Aachen, he was also kind of starting a bit, let's say, or getting more serious with getting into CFD, computational fluid dynamics. Yeah, in this part, Philip and I want to go a bit on our tools and what we can do with NGSolve and our tricks that we have inside to solve Navier-Stokes equations, essentially. And yeah, we will essentially split this into one big part about Stokes equations and how to solve that efficiently with parallel solvers, iterative solvers, and so on. And then also to have a part on time stepping and how to solve the instationary Navier-Stokes equations. Okay, so yeah, let's start with the PDEs just to get us into the picture. Most of you will know this. So essentially, we're looking for a velocity field vector value function u and a scalar function, the pressure p, solving that set of equation where the first equation is essentially the momentum balance, so balances of forces. The second equation is the mass conservation, where yeah, we assume that we have constant density, so we have an incompressible flow. Of course, you can go through compressible flows as well. We will also have a talk contribution on that within the user meeting. But that's essentially all that we are going to cover in this session, and we'll concentrate a bit more compared to the variety that we saw in the models in the solid part, a bit more on kind of the techniques and kind of the optimization steps that we take to get good solvers for that. Okay, so this is essentially the start. So what do we have? Which type of difficulties do you get in Navier-Stokes equations? So we have this divergence of sigma. So this is the stress as you've seen before. So now let's say this for the simplest model, and this is what we're typically dealing with, the Newton fluids. It's essentially that your stress depends on your velocity instead of the displacement. That's kind of the switch that we have here. But apart from that, it's very similar structure. We have the strain tensor essentially here. And yeah, you can rewrite this to the Laplacian, except for boundary conditions, but in many cases, essentially that's what you do. So you have, for the viscosity terms, you get essentially from the stress thing, you get essentially the Laplacian. So this is kind of your diffusion operator vector valued in your equation. That's, I would say, the most simple part. Then you have difficulties essentially coming from the saddle point structures. So you have the pressure part as well in here, which you can see as a Lagrange multiplier for the constraint, which is the mass conservation. And then you have the convection part here. So this is the transport of the momentum due to the velocity. So that's the nonlinearity that we have in here. And typically, you also have that this can be quite the dominant part compared to all the other effects in your equation. Okay, so this is kind of a preliminary start. I guess most of you have seen this to some extent. Then if you want to complement the system with boundary conditions, you have different choices. And you will also see that some of these are more natural for some methods than others. So of course, yeah, we can have directly boundary conditions for the velocity. essentially prescribing that there's no flow neither through the boundary nor kind of tangential on the boundary. So this is the standard no-slip boundary conditions that you also kind of typically think about if you have flow at a wall or something like this. You can also prescribe non-zero boundary conditions. If you have an inflow and you know kind of how the flow enters into the domain. And you can also have boundary conditions in terms of the stresses. So the standard, or the famous do-nothing condition, essentially coming from the weak formulation of the problem, means that there are no stresses, often used as outflow boundary conditions. Okay, and this type of conditions we want to prescribe. So the roadmap is that we want to start talking about the Stokes equation, then doing conforming discretizations, talking about iterative and parallel solvers, going to our more kind of favored discretizations for this set of equations, the normal continuous, so H-diff conforming discretizations, and then we'll discuss a few tricks and tweaks to get these methods implemented efficiently, and then we'll go to time stepping of these methods. Okay, so first simple step, we go to Stokes equations. This is what we have here. So we throw away the convection part, we throw away the time derivative part, and what we are left with is essentially just the compatibility, kind of the divergence constraint, and the Lagrange multiplier, and the viscosity in the system. The weak formulation then takes this form. So we're looking for velocity in H1, plus minus boundary conditions, and then we have a pressure in L2, which is kind of the compatible space in that setting. The weak variation formulation then takes the following form. We have this structure that we have what I call the A block, right? So we have a bilinear form related to the viscosity, and you have a B block where, now you see the gradient P turned due to a partial integration to the divergence V. So this is the symmetric part to the weak form of the divergence constraint, and this is what you see with the B bilinear form here, where you have the pairing between U and Q and V and P. Okay, so far so good. That looks like a form that you can easily apply finite elements for. And indeed, that's the first thing that I want to do here. Very simple stuff. We take a look at function spaces that are finite dimensional, that are subspaces of our continuous setting. And the most famous example probably is a Taylor-Hood element, where you take polynomials of degree. Oh, yeah, that's wrong. So so before we had pk and pk, and now I corrected this and I put the k-1 to the wrong side. So this is velocity should be on pk and the pressure should be on pk-1. So because you want to have the higher regularity, so if you take the derivative of that, kind of you want to have still enough degrees of freedoms compared to what you have in the pressure space. Okay, anyhow, so pk and pk-1, this should be kind of the standard choice. Both continuous functions, so especially continuous pressures. And now we want to kind of solve this now for the first problem. So we take some, not too trivial geometry. So this is a NACA airfoil. So there's this kind of large set of different airfoils that you can set up. And then we want to set up the problem. You get the vector valued H1 space, order 3, and pressure space, order 2. So here is correct. So we have higher order for the velocity than for the pressure. And you set up just kind of usual manner the corresponding bilinear form K, consisting out of the A block and the two B parts that we have here. Okay, then you solve for this. So here we just do this with a direct solver. We get essentially our first 2D example solving the Stokes equations. So this is with boundary conditions prescribing inflow from the left, then flowing around this airfoil in that example. Okay, that's the very basic start, and now we hand over to Philip to get more interesting.
Shortly introduce who is Philip. Okay. Yeah. Ich bin jetzt Philip. Philip did his PhD on numerical methods for fluid dynamics, picked up from the H-diff conforming HG method to the mixed method called MCS. Mixed method we will see later. And very recently, Philip got started a move. He is now a professor in the Netherlands in the Twente University, staying there for a year. Let's see what will be next. There's some rumors are going around.
Yes.
So,
thank you very much.
Okay, then looking for Philip's part of the Stokes part.
Yeah, thank you, Joachim. So, Yeah, that's a cold start now for me. It's somewhere in the middle. Okay, so the main idea was now that we have somehow started with the Taylor-Hood standard method with a direct solver, and the question is now how can you go big here? So we try to set up here now an iterative solver, a parallel solver. So the main idea is that we want to do again a NACA airfoil, but now in 3 dimensions. So you might, the number of degrees of freedom might increase significantly. I think I can do one more, right? Good. Okay, and the main idea here is that we want to use a preconditioned MinRes or GMRES Krylov subspace method. And the question is now, how can we set up a proper preconditioner for our saddle point problem? So obviously we cannot use, so this was our K matrix. So here you see again this A block, which corresponds to the diffusion, and our 2 B blocks from B and B transpose, which comes for the divergence constraint. So this was the corresponding finite element matrix that popped up from the system from before. And now we wanted to solve, or we want to find a preconditioner for this indefinite system here. And the main idea here is, or to motivate what we are going to use here, is that we can actually factorize our K matrix in this following form here. Where here, that's somehow crucial here. So here you have this A block from before. This is this diffusion matrix for our velocity. And here on the lower right side, so in this lower block in the corner, you have the so-called pressure Schur complement, which is this B A inverse B transpose. I will come to that back in a second. So the question is now, how can we solve this? And the main idea here is somehow you see already this block diagonal structure here. And then the main idea here is now that we hope to somehow have a proper solver. So a preconditioner for this A block, which we will always denote by this hat. So this A hat should somehow be spectral equivalent close to this A. But it allows an efficient application of the inverse. And similarly for this S. And then the main motivation here in a first step is, okay, so we have this structure here in the middle, so why not use a block preconditioner that has this following form, where we have now replaced this A by this A hat and the S minus by this S hat. This will be a first idea, a first approach that we are going to consider. We will later on also look at a different block solver. The question now is, of course, what can we choose? What can we choose now for this A hat and the S hat? And as a first step, I want to talk about this S hat. So there is a little bit of a hand wavy now included. But the main idea here is that we want to look at this pressure Schur complement here again. So this B A inverse B transpose. And when you write this down, you can somehow see this as, so this is the divergence operator, then you have this new inverse Laplacian inverse, so which corresponds to this A matrix, and then you have the B transpose. So you have, bear with hand wavy, a derivative here, and here you have 1 over 2 derivatives. So the idea here is that this somehow is pretty close to a mass matrix with a new inverse here. So the idea here is that probably a pretty good preconditioner or a pretty good solver for that lower block here is the mass matrix on our pressure space with 1 over the viscosity scaling here. The question is how or when can you do a pretty good inverse here? And of course we want to do all of this in NGSolve later on. So an idea here, if you use, for example, a Taylor-Hood element here, is to use a mass lumping. So you have a diagonal here, or you can do different types of things here. Okay, so we want to do this in NGSolve, and probably you haven't seen this implementation yet so far, so we haven't done MPI yet. So this is pretty easy here in this Jupyter notebooks to set up a cluster somehow. So you see here we will actually start a cluster with 4 MPI ranks. So here with this MPI ranks you can start the cluster. There is some coding here around to somehow that it is possible for us to build this for these books here. And you see here now we have started 4 engines. So this is again just for a demonstration here. So we have now a cluster of 4. Yes. Oh no, we are coming there. We will come there. I'm not there yet.
Because you need the input, right? For
there's a note.
There is a note. So for things that I'm not mentioning, there is a note. So yes, this spectral equivalence depends on the LBB condition. Sorry? No, but it will be probably seen in the number of iterations then later on. But I think Joachim wants to add something. Or no? Okay. But I will come to the discretization in a moment. Good. Now I'm lost. So we have started our cluster, and the crucial thing is now in this Jupyter books that you have to use this thing here at the beginning. So if you add this to your cell, thank you. This is actually done on each of the nodes. So this is crucial because if you forget it, then you will get strange comments that something is not defined, and you're wondering, I've imported NGSolve, but now you don't know the vector H1 space suddenly. So yeah, I was there. Okay, so what we have done now here, so on each of our nodes, we want to now import the MPI. So we import MPI for pi, NGSolve netgen, that's somehow clear. Some solvers, so what we are going to use is the MinRes solver, the GMRS solver, and something more that I'm going to talk about later, which are available in this package library or as part of NGSolve. And what is also crucial is this from NGSolve, now this interface with PETSI, so we are going to use a PETSI solver, where we will hear more today or tomorrow. Today, later. So if you have any questions, please don't ask me, but back there then. But this is the main thing. So I'm very happy to do some nice methods, but the solving routine here on that part, yeah. Yeah, let's keep it just like that. Okay. Yeah. Okay, so then we do again the NACA profile, similarly as before, but now in 3D. So there should be somewhere a comment. Now the dimension equals 3. You see at some of these cells there are still some things commented out. So feel free to comment on that. Okay. So let's discuss what we want to do as a discretization and how we can set up the corresponding preconditioners. So in the first step, so you see here already our plan, we start with the Taylor-Hood, and we want to first mainly discuss the iterative and parallel implementation for the Taylor-Hood element. So yeah, we're considering the Taylor-Hood element, and the main idea here is in the first step that we want to find a preconditioner for our A. And for this, in the first step, we realized that, so we have in 3 dimensions, we have 3 velocity components, and we have a vector-valued Laplacian for our, I don't have it here now anymore. So basically, we realized that our A systems, our diffusive matrix, is actually block diagonal, where each of these blocks is the same one for each of these components, for each velocity component. So you have here the x velocity, the y velocity, and the z velocity. And each of these corresponds to now scalar Laplacian. And we want to somehow use this also in the setup for our metrics, and also in the setup for the preconditioner, because the main idea is now that we somehow, when we want to find, so remember this is our main idea, we want to somehow find a preconditioner for this system here. So what we basically want to do is we want to find a preconditioner of these small blocks for these scalar blocks, which as already mentioned, we are a PETSI solver, so that's the nice thing. We can use PETSI solvers for H1-like problems. So this is crucial. We are going to use the Taylor-Hood element method. So we're using a H1 conforming method, and there we can use then really the PETSI solver, which will be available in NGSolve via this GAMG flag. Okay, so we want to set up this system now. How can you do this in NGSolve? And as we will later see, when we are going to use the Krylov space methods that are available in NGSolve, so that MinRes, for example, we are going to use block matrices and so-called block vectors. So these are from NGSolve to set up our system and also to set up our preconditioners. So that's crucial here. Yeah. Okay. All right. So. The question is now, how can we actually set up this system that is somehow this tri-diagonal blocks? And for this, we will actually use now this vector H1 space that you have already seen before. So this is the vector H1 space for the Taylor-Hood approximation. So you see here order 2, order 1 now in this case. So again, the polynomial order is correct here. And we also set up H1 space for the scalar variables. So you see now here we have a vector H1. So this is it has 3 components. And here we have now the scalar component. Good. Okay, now we want to set up this bilinear form. So we have now, we just set up the bilinear form on the scalar space. So this is the bilinear form A1. So this is on the scalar space. And we also later use this B constraint, which now actually is defined on, again, as for the Taylor-Hood element before. So we have our V and a Q space, so with the corresponding trial and test function. This is our B operator. Okay, and the main thing now here that is crucial is this het A1. So this is now the preconditioner that is defined for the scalar part. And you see here in NGSolve, that's pretty easy. You just write preconditioner bilinear form A1. So this is the one on the scalar, for the scalar variable. And we add now this GAMG flag. And when you call the assemble routine, then also the corresponding preconditioner will be set up. Okay, and as mentioned, so now we have this scalar part, and now we want to define the corresponding preconditioner for our vector valued A, for our vector valued block. So for this capital A tilde, so the which corresponds of a solver for each of these scalar components. And the main idea is now that we are able to use embeddings and restrictions which are available by this vector H1 space. So which allows you to get an embedding and the corresponding components for each of corresponding components. So you see now we just use the precondition that we have already defined now, and now we can use here, for example, the v.embedding 0 will give you the corresponding first component, and the v.embedding 0.transpose will be the corresponding other part. So when we sum this up, we will get this matrix, which will be done here now. So you see here you have this. We take a sum matrix of the corresponding matrix and preconditioner that we have just defined, and then we use our restrictions and our embeddings for the big systems. Good. Questions so far? Please feel free to interrupt me. Yes? No? Yes. Good. So for the pressure matrix, so now we also have to set up this this S solver. So we define now. The idea was, remember, we have our spectral equivalence to the mass matrix. So we have this P times Q and 1 over nu. And now we have this flag diagonal true. So here we will use this mass lamping. You can also do this with integration rule, but here that's pretty fast forward, and we take the corresponding inverse. Okay, and now here you see that we assemble our system. What is with zeros?
Yes, in the integration rules, and you are storing also the zero elements. And
indeed.
Is not so cheap.
That's true, indeed. Okay, then you also have, so you have now, we have our B block, and we can now set up our system matrix that we have for the Stokes equations from before. So we have this A, this B transpose, B0, so this is our system matrix. And correspondingly, so now for the right-hand side and for our solution vector, we also have to use corresponding block vectors. So here we have our system matrix, and our right-hand side will correspond to a linear form vector that is defined for the velocity part, and a linear form vector that is for the pressure part. Okay, now here you see that we actually set up our block matrix and our block matrix block diagonal solver. So here we have now the solver for the A, and here we have the solver for the S. Good. This is more or less the same as so you probably know this already. When we have some boundary conditions on the right-hand side, we do a homogenization. So basically we have our right-hand side minus k times boundary condition. So this is our right-hand side vector, so nothing special here. We set up our grid functions on the corresponding spaces on V and Q. And now here we have our solution vector. You see now this is the block vector with the corresponding vectors of our grid functions. Okay, and here we now have our solver. We have our MinRes solver with the preconditioner, the matrix, and we do pretty, and then we apply the solving routine. For some reason, yeah, here down you see it now already. So we are now also able to, thanks to Matthias, to have some field lines. So here you now see the solution of this three-dimensional flow around this NACA profile. It's unfortunately it's a little bit dark, but yeah. So this is the field that we were looking for, the velocity field. Okay, so this was a block diagonal preconditioner. You saw now already that having the availability for these block structures, you can do some more fancy stuff, and there are many available. And we now choose, for example, this Brest-Sarrazin block preconditioner. One thing. Oh. Okay. So basically the main idea is, before we just took that into consideration, now we also include that by basically changing here this A heads and now also including this A heads here. And then you see basically that your preconditioner consists of these two parts. How much faster should I be? Okay. Okay, so the question is now, how can we do an application of this preconditioner? So before we had just this the matrix, this tridiagonal matrix. We could, of course, set up it again as before, but this is then super slow because we have quite a lot of applications of the A inverse. Actually, we see that an application of this whole system, then you can reduce it actually to solving such kind of a system. So this system is equal to that right-hand side. So the basic idea is that you can then solve this by these three steps. So you have to be able to have somehow you have to be able to have the vector for the linear form f and the linear form g. So we have this already with our corresponding components. We have our A solver, S solver, and again the A solver. So now we have these separate components, and we can actually somehow implement now a proper application of the inverse or the multiplication of this vector. And this you can do I mean, there is a lot of additional stuff because I have copied that from another thing where we use a little bit more. But basically, you can introduce a new class as a base matrix, and you can overload the multiplication. So this is the crucial part I want you to look at. So we have an input and an output. The input is the f and the g, and you see now here we do first an application of the inverse, then g minus b blah blah blah. And basically, this is just this multiplication written down here now with the corresponding vectors in NGSolve. And then you can do the GMRS solver, and you see now that we have much less iterations. Okay, still we have now used the MinRes solver and the GMRS solver. Surprisingly, if you do it correctly, you can also use CG solver for saddle point problems under certain conditions. So this is this Bramble-Bashir conjugate gradient method. And the main idea is now that when we have some kind of a preconditioner for this A block that we already had before, and we have a proper scaling, so a spectral equivalence, then you can do some magic transformation and get this kind of a system. And then you can show actually that with, where is it? You see, yeah, we show that this M is a symmetric positive definite system. So basically you can then use the CG solver. The crucial thing here, so now we also have a warning, not only a note, that the alpha has to be really 1. So in this Bramble-Bashir CG solver implemented in NGSolve, basically what we do before is that you see this in the output here. We do a short solve we do a short eigenvalue solve to allow a corresponding proper scaling, and then this works here. Okay, so this was the iterative and parallel implementation. Yes.
Find out that GMRS is being part in one, because I was trying to do exactly what you showed yesterday, use the C++ +1 and fail miserably. So
Say again, please.
the GMRS needs to be the third GMRS.
Ah.
The C++ is the one.
Indeed.
Thanks for mentioning.
Yes. Just use the one that. Yeah.
And we see the discussion already starts with the parallel game from the backside. So Umberto will talk more about the PETSI interface in the afternoon, and also Lukas Kogler, he has the parallel MG from NGSolve, which is now already available, will also show one parallel solver. So we have
Yes.
time and options to discuss.
Good. We have not a lot of time left, or not that much time. So now we have finally brought Taylor Hood behind us. So now we can do a little bit more fancy method. So yeah, this was the method that Joachim and Christoph did a lot before me, of course. And yeah, let's go over that a little bit. So the main idea here is, or the main motivation is that you can, when we want to go to Navier-Stokes as well, we have this convection operator included. So we need some kind of a stabilization mechanism. And what we want to do is here we want to use, first of all, an upwinding scheme. So this is why we want to go to a DG or HEG method. On top, we want to use this HDiff conforming method because it allows an exact conservation of mass. I don't want to go too much into the details, what are the nice things here, but particularly we have also energy stability, which will be crucial for the convection dominant regime. So when you really have, as Christoph mentioned at the beginning, when this convection operator might dominate. Okay, so the main thing here is now we want to have, we actually have two spaces, so we want to do an HEG method. You already saw this in detail probably yesterday. In the HEG part. So now we have HDiff conforming velocity space. So again, here is the k missing, great. So we use polynomials of order k in d dimensions that are normal continuous. So we have this HDiff space here. And we have also facet variables which are in the tangential plane of order k, which is missing here. And the crucial thing is we choose now for the pressure, we choose polynomials of order k minus 1. And then we get this, I thought actually it is here somewhere. Yeah, we get this nice property that the divergence of V is a subspace of the Q, and by that we get this exact conservation of mass. So as mentioned already, so you have seen this probably yesterday to some extent. I don't know how much details you have seen. But basically we now reformulate our Stokes equation that we had at the beginning. Oops. With our, okay, now the scale is a little bit tricky. So here we have our A block and we have our two B blocks again. But now the crucial thing is for this A block we have to use some kind of a symmetric interior penalty, for example, method. Okay, the nice thing is now with this, so maybe let's go up to the spaces, is that Christoph mentioned at the beginning that different boundary conditions are better suited for certain methods. And as an example, here we have now that the natural trace operators for the HDiff space and this tangential facet space are the normal and the tangential component. So particularly when you have, for example, slip boundary conditions on curved surfaces, where you really want that the normal continuous part should be 0 at the boundary, this is can be very easily done with this method, whereas with a Taylor-Hood method it might be a little bit more tricky, or it is more tricky. Okay, so we want to do this with a simple example here. So basically we have this cylinder here, and the main idea is that we have 0 boundary conditions, complete 0 boundary conditions at the top. We have some rotating boundary conditions at the bottom, and we have slip boundary conditions at this surface, so at the side of the cylinder. And this is now very nice that we can do this with the velocity space. I will skip this here now because this is not so important. You can read through that. We have now this HDiff space, we have the tangential facet space, and we have our pressure space. And the crucial thing here is now, again, maybe this block from before. So we have now this K block again, which is the gradient U, gradient V, plus this divergence constraint. And now we have here this additional lines, which comes from the HDG method. So this is probably clear. Again, now we do here a direct solve. Okay, and you see here now a first step of the solution. So what we have here is a right-hand side. Sorry, I have skipped the right-hand side. Okay, no right-hand side yet. Okay, so you see, so we have a 0 boundary condition at the bottom, and we have a rotation at the top and a rotation at the bottom. So you see now that we have somehow this rotational flow field, and you see here these field lines. Okay, now we want to add a right-hand side as well. So now we have this F, and you see here that the force is showing downwards in the center, so it somehow shows down here, and it shows upward at the boundary. So we hope to see some kind of recirculation here. And what we did here now is, hopefully, is that So I have to switch here now. Okay, so we increased the strength of the velocity in each step. So what you see here at the beginning is you see like the circles in that direction, and then slowly it rotates and the force gets stronger and stronger, and then you see really these circles, so this flow that goes in that direction. So probably from here you see it very well. So at the end you really see these circles that appear due to the force going down in the middle and up at the side. Okay, how much time do we want to spend on the parallel solve? Okay. Okay, so just a very short comment. You can also do a parallel solve for the H-diff conforming method. The problem now is that we don't have an H1 conforming space, so we somehow be able to use the solver, for example, by PETSI, which are just available for the H1 space. And the main idea here is that we use a so-called auxiliary space preconditioning. So this was a lot of this was also done by Lucas. So basically, you do use some kind of a smoother that you can do for NGSolve for the H-diff space. But here now use an embedding, and this embedding is basically an embedding from the H1 space to from the H-diff space to our H1 space. Here we can use now the solvers that are available by PETSI, and then we go back. Probably this is just very, very fast. There are a lot of comments here as well. Yeah, I think I will skip that now due to time reasons, because otherwise you won't see the fancy part. Good. So yeah, there is. So you see, you somehow have to assemble these embeddings. There is a lot of comments here that you can find. So here you see this embedding operators from the continuous space to the H-diff space, and from the continuous space to our tangential facet space. It is set up as the sum here. You do some smoothing as well, and then you basically just solve this. No, wait a second. Why? Because I'm in the wrong thing. Now I would have been disappointed. Good. So basically, at the end, you can see something like this. So this is a step file. So you can also include step files in NGSolve with this OCC geometry. So here we have a flow around an airplane, and we have solved this iteratively on our cluster. Good. Ach, mein Mikro.
Okay, yeah, so what we've seen now is essentially that our favorite method is not H1 conforming, but only H-diff conforming. And the price that we have to pay for that, I mean, the benefits are that we're quite a robust method, robust in convection, robust in pressure forces and things like that. So very nice method. The price that we have to pay is the non-conformity, and that comes with computational cost typically. So the one thing that we've seen is that we use hybridization, so we have facet unknowns that have the purpose to decouple essentially from one element to the other. Sure, I can try. Okay. Yeah, so essentially the idea of this hybridization is always that we avoid the directly decoupling from one element to the other and introduce this intermediate layer. And there are still a few other tricks that you can do, and this is what I want to present here. And there's a kind of a special section that I dedicate to J, because essentially that's one feature that did not have a nice documentation so far, and on the fly I want to briefly mention that at least. Okay, so let's take a step back and just repeat essentially what standard hybrid G looks like, and this is now for the scalar case to make things a bit easier. So here you see essentially you have polynomials with, there's a pk, that's okay, for you, Philip. So we have now on the volume pk, on the facet pk, polynomials which are apart from that discontinuous across the mesh, and you do an interior penalty discretization. So you have the standard volume part, and then you have gradient on the boundary, at times the jump between element unknown and facet unknown, and then the corresponding penalty to make things coercive. Okay, and that you can solve for. Scalar problem, everything looks nice, nothing super complicated. So L2 at facet space. The remainder is pretty simple. So what we always do here, which we haven't discussed too much yet, is that we can do static condensation. That means we know that all the volume unknowns, so the whole function that live in this L2 space here, that they just depend on the facet unknowns. So once you know the facet unknowns, you can completely reconstruct the element unknowns, and that leads to the fact that in a linear system, you can form the Schur complement strategy to end up with a global linear system just for the facet unknowns. Okay, so that means the facet unknowns are determining the major cost in solving these type of linear systems. Okay, and there's one trick that that we can do. So if you take a look at the formulation, you might see, if you think about it a bit, that here the one part of this boundary integrals that we have here, they just appear, so this gradient u dot n appears just as a polynomial of degree k minus 1 due to the derivative. That means the pairing between this jump and this gradient stuff, is actually, you can project this down to pk minus 1. And that means that the facet unknown, effectively, you can reduce to something up to degree k minus 1, and thereby kind of reduce the number of unknowns in your global linear systems a bit. So this is a bit more in detail explained here, but the major idea is that in the stabilization term, so this jump term, you introduce a projection to k minus 1 in order to just involve the facet unknown up to that corresponding order. And now the question is, how can you implement this jump term? And there's the nice trick. In many spaces in NGSolve, you can find this kind of flag, highest order DC. So DC stands for discontinuous. And here for the facet space, this means that we have, the following picture perhaps helps to speed this up a bit. So we have unknowns on the facet of order k. And now we can split these two up into polynomials up to degree k minus 1. So this is the red one. And the highest order ones that are polynomials up to degree k, but orthogonal to the pk minus 1 degrees of freedom. And now the trick is if you do this highest order discontinuous, you split up the unknowns on the facet, the highest order ones, so the green ones, into two parts belonging to the two neighboring elements. And then they become local unknowns. So they are associated no longer to the facet, but they are associated to the element. Okay, why is this helpful? Yeah, so if you take a look at the corresponding formulations, you can figure out that the equation that is left for this highest order part actually implements, so this is this u bar hat here, this actually implements the projection into the orthogonal complement of the jump. So it means effectively what you have in the jump, so u minus these together are the facet unknown. This effectively means you have u minus u hat. This is the k minus 1 part. And now here you essentially subtract the projection, the orthogonal complement. So effectively this implements for you the projection into the polynomials of degree k minus 1. Okay, so perhaps if it's a bit fast, you can read this up later on. But effectively, this trick gives you essentially a projection that you need in order to do the reduction without adding consistency errors of lower order. Okay, and now this trick is essentially what, if you want to implement this, this is what you do. So this v hat is a standard facet space, and now with the highest order DC, we have this v hat s, so s for star. And now you can check essentially degrees of freedoms. So what happens now, v hat has a certain number of degrees of freedoms here, okay, correspondingly degrees of freedom per edge times the number of edges in 2D. And now we do this other thing, and we actually get more degrees of freedoms. This is because we essentially duplicate the highest order degree of freedom, right? Okay, so a small catch, essentially the difference between those two is 319, but the number of facets is 395, so that doesn't match up. Does anyone have an idea why this could be the case? Boundary, exactly. Yeah. So on the boundary, we don't do this, so we don't need to break up continuity because these boundary degrees of freedom don't have any coupling costs in that sense. So here's kind of the solution. So boundary facets are untouched. Okay, good. So the more important question is the degrees of freedom that remain in the global linear system, and these are the lowest order ones. So the lower order one. So k minus 1 degrees of freedom. So if you now count the Friedhoffs, so these are the degrees of freedoms that are remaining on the globally coupled system, and Friedhoffs with coupling equal to true, then you see that you go from the one space to the one with the highest order DC, you actually really reduce, so you halven the number of degrees of freedoms in that system. Now this here in this case is halfen because it's order 1. And then you have order 0, so that reduces by a factor of 2. But of course, for higher order, the numbers are different. Okay, so this is the one thing. So this is giving you actually more or less the same qualitative results. There's the next thing, hidden DOFs. So I already mentioned essentially that we have local DOFs, so we have degrees of freedoms that are associated to the volume, so in the interior, that don't have a direct coupling with neighboring unknowns. Then we have interface DOFs. These are the unknowns that remain in the global linear system. And these kind of distinguishing between those two types is important, for example, for doing static condensation in a very generic way in NGSolve. So now we also introduce hidden DOFs. What's the idea? The idea is that we have this highest order unknowns introduced, but we actually don't need them in the solution later on. And so what happens on the facet, we actually don't care too much about, so especially not the highest order component part. So can we get rid of this part of the finite element space in the first directly? And here comes kind of the idea of hidden DOFs into play, saying that there are degrees of freedom that we might need for setting up some local problems, so for element matrices and so on, but we might no longer need once we kind of set up local parts. And that's the idea of hidden DOFs. So there are some essentially criteria that you need to have in order to make use of them. So you need degrees of freedoms that only appear on one element, so there's no involvement on neighbors. You only need them during assembly, so no reconstruction later on. And also the linear system does not have any right-hand side related to these degrees of freedoms. So if you have this, then you can make use of that. Okay, so where does it play a role? Well, let's perhaps do this in the other order now to speed things a bit up. So what you now see is we introduce two other spaces, finite element spaces. The one is having the highest order C, and a new flag that says hide highest order discontinuous one. So that means these special degrees of freedoms, they are now getting this hidden DOF flag. And then we do the compress. Now this is a wrapper that says, okay, I essentially remove these unknowns from my vectors to really get a smaller vector and smaller dimension in my linear system. Okay, so let's see. So here we have V hat. This is the standard facet space order 1. V hat S is the one where the highest order is split into the two parts. Then we have the one where we mark some of them as hidden DOFs. Doesn't change the number of unknowns yet. Only after I use the compress, I get down to essentially just one unknown per facet in the case of P1. Okay. So far, so good. Any question at that point? So now the question is, at which places are these kind of flags used? Yeah. So to get the method done, we have the highest order discontinuous flag now introduced. We have introduced the highest order thing to get this hidden DOF thing activated, and we use the compressed in order to reduce the number of unknowns in the vector. So important is to understand there's a different point of view on these degrees of freedoms from a local perspective and a global perspective. If you set up element matrices, it's not important if you have a hidden DOF or a local DOF or whatever, you kind of see this part. But then when putting this into a global system, there's this situation where you have to distinguish these things. So what I do here is now I run over this space for all these different spaces. I run over all elements. Actually, I just skip after the first one so that we have one local element. And there I ask for the degrees of freedoms that pop up, and I ask for the type of this degree of freedom. So what you see for the standard method is now you have, on one element, you have essentially 6 unknowns. And for the first method, this is the first column, you have some numbers, okay? And these have the different types, wire basket and interface. Wire basket is kind of a special interface DOF that is kind of used for some preconditioners. Doesn't matter, so these are 6 interface DOFs. Now if I say highest order discontinuous, I still on each element have 6 unknowns. There are 6 because it's 3 facets and it's 2 unknowns for the P1 on an edge. Then you see already that one of those now is only local. Yeah? So that means it's not involved in neighboring couplings. Now I go this highest order, then the local ones get hidden DOFs. And now if I use the compress, then there's actually no association to any global vector anymore. So that means there's actually degrees of freedoms that are locally existent, but they are no longer globally existent. That's kind of the trick with these hidden DOFs. Okay, so now we can apply this with all these different versions. So standard facet space, plus highest order DC, plus hidden, plus compress, and you see different type of effects. So what you see in the number of degrees of freedoms, they actually, let's say, these are getting more. until I compress, then they're getting less. But the more important part is what do you have in the global linear system. So these are the coupling degrees of freedoms, and these are reduced as soon as I use this highest order discontinuous flag. Correspondingly, the non-zero entries in your Schur complement, these are also kind of reduced directly from the get-go if you use that flag. Only the dimension essentially of the vectors and the dimension of the matrices, they also change accordingly to the other flags. Okay. Good. And then there are some further details, essentially. How do you set up the systems? So you can do static condensation. If you do static condensation, then essentially you just do static condensation as usual, with where hidden DOFs essentially are just vanishing. So you essentially don't get the result of the static condensation in the global system back. If you don't want to do static condensation, which you could also do, and you still want to make use of the hidden DOFs, then you can call what is called eliminate hidden to your bilinear form. Then essentially we just form the Schur complement with respect to the hidden DOFs. So if you think about an element matrix, you in general have this type of structure. You have interface DOFs, local DOFs, hidden DOFs. And for the hidden DOFs, we always know that we have a right inside 0 here. That means we can always form the Schur complement, and that's what we want to do. So we want to have the local influence of these hidden DOFs and get the correspondingly transformed matrices through the Schur complements with respect to them. And then we can continue and either also do the Schur complement with respect to the local DOFs. Yeah, note that if you do this for the local DOFs, then you want to recover the local DOFs later on, so you have to store the factors in the Schur complement strategy. While for the hidden DOFs, we don't have to do that because we don't care about them later on. Okay, so that's kind of the gist of it. So essentially, these are the ways that you can deal with that. So you can do a full static condensation, you can do just eliminate the hidden DOFs, or you don't do anything at all. But if you don't do anything at all, then you have to be careful, because then this might not give you the right results if you really have hidden DOFs. Because for the hidden DOFs, yeah, you don't have any global association later on. So if you set up your element matrix, essentially the values for the hidden DOFs, they completely kind of are not used correctly. So that's kind of the thing where you have to be careful. So if you have hidden DOFs, then you should at least use eliminate hidden. Otherwise, you might get not what you want. Okay, so here's now a comparison essentially of these things. I'll skip to that. But essentially now the same as we saw before, now with the different type of Schur complement strategies. So either no Schur complement at all, just for the hidden, or the full one, and then the different corresponding numbers. Okay, I'll skip through the lifting. So there are different other cases where you might need hidden DOFs. So here's an example based on lifting formulations of DG, or in this case hybrid DG formulations. You can read it up if you're interested. It also kind of uses then the hidden DOFs, where the interesting part might just be that your space gets this flag hide all DOFs, so that you can completely set a whole space essentially as being just an auxiliary local space. Okay, so let me see, is there anything very important? Otherwise, I would rather skip forward. Yeah, so here there's a warning. I already mentioned that. Okay, so that's kind of the idea. And now we are really getting short of time. Okay, so just a few mentions at least. So this is for the scalar case. Of course, we want to do this for Stokes now. Let's think about what does it mean for Stokes. For Stokes, we have HDiff, so we have normal continuity, and for the tangential component, we are not conforming and do this hybridization. So we have tangential facet unknowns for the tangential part. So we have the tangential facet space. And now you can do the protected jumps also here, doing essentially the same as before. Yeah? So we split highest order from lowest order ones. So just to mention this in the larger context, you can also do this for normal facet FE spaces. So you have this kind of flags and this kind of, let's say, idea for different ones as well. If you think about kind of optimality in terms of degrees of freedoms, you have that the normal component still is order k, and in that regard, slightly suboptimal, so a bit too much if you want. So there's a compromise between, let's say, the perfect compatibility in mass conservation and so on, and kind of getting the reduced number of degrees of freedom in your global linear system. So what you can do is you can actually relax the normal continuity to just be normal continuous up to order k-1 and do something with the highest order. again and split this up. Yeah? So this is essentially what you can do here. So if each of these blue things is 1 degree of freedom, then for order 2, you would have 3 of these degrees of freedoms. And now you can split them essentially orthogonally, L2 orthogonally in terms of their normal components. And then you could kind of just split this one thing up into 2 parts associated just to elements and no longer to the global interface degrees of freedoms. Okay, and again, the flag for this is highest order discontinuous. And also here, you will use you can use this with many other different finite element spaces in NGSolve. Okay, with that kind of reduction, you have to be careful about what to expect from your method in terms of these nice properties, and you can essentially recover some of them. I will skip through that. You can also reduce some additional degrees of freedoms. If you know a priori that your solution will be exactly divergence-free, then there's this highest order divergence-free flag that kind of removes some degrees of freedom a priori. You can also reduce the pressure space a bit. Let me perhaps skip on that. You can read it up if you want. And essentially, kind of the final thing that we can have is this large table where you can now ultimately compare different type of options. So you take finite element space, the standard one, so the one that Philip already discussed. Now we do the projected jump, so the highest order discontinuous for the facet space. We do this not for the facet space, just for the HDiff, or we do both. And then we also have this kind of combined with this highest order discontinuous, higher order diff-free setting. This gives us 8 different methods, and on the left you have the different types of elimination of degrees of freedoms in a Schur complement. And then you can compare degrees of freedoms in different spaces, coupling degrees of freedoms, number of non-zero entries, time for assembly and solve, time for solving, and time for assembly. And then you should essentially figure out that if you apply all the tricks, you get the cheapest method of all of them.
Is accuracy more or less the same?
Yeah, that's the key point of in what we do, essentially, exactly. Yeah, so to do everything with a consistency error that is pretty much higher order in all these
It's
buildings.
the same order. But
Yes.
Maybe
Yeah.
constant 10% better? Or like
Exactly, yeah. That's true. So you might lose some constant there. Okay, so that would be it from my side, and we can skip to the more results that we get in terms of computations, right? So, any questions?
Fancy pictures. Moving pictures.
Jay? I don't know where he is. Are you happy with the hidden doves? Yes. Good.
No, thanks.
Yes.
For these reconstruction operators, this is hidden post-processing.
Yeah. What was it? Sorry?
Do you bring the dots for post-processing and another computation?
Yeah, you could know that if you put the hidden dots into your system, you will not recover them later on. Right? These are different.
very good hidden.
They are too much hidden. You will never see them again.
Okay, so at least a few comments about the full Navier-Stokes system. So basically what we do for instationary Navier-Stokes is that we always use, or normally use, this IMAX operator splitting method. So there is a lot of more information on how this is done in the NGSolve docu. So there is a link here as well. So basically so this is more like an application now. We wanted to solve, or I always wanted to solve a flow through such a Tesla valve. So I'm not sure if you have seen that before. This is by Nikola Tesla, was suggested in a patent. And the main idea is you can have a flow from the left to the right or from the right to the left. And maybe we go first here. So when you have a flow from the right to the left, you basically see that it can pass through here and more or less has a laminar flow profile. Whereas when it goes from the left to the right, you see, okay, somehow it's getting divided here, and it turns around here, and since it's turning around here, it somehow will stop itself. So that's the main idea, and you do this again and again and again and again. And this was the main idea of this Tesla valve, and I always wanted to see if this really works. So Christopher doesn't know that I have modified the file a little bit. I hope that this is not breaking your part on that. But basically, so with this OCC geometry, you have now the access to also build these very beautiful geometries. So here we now have this valve. So the valve basically is the one in the middle. And in order to have a flow profile somehow here, then we actually close the valve here. yeah, for reasons. So the main idea is now that we want to approximate this flow inside the system. So we have a right-hand side, and the idea here is that we have a right-hand side that, will be activated or will be like a driving force in the interior of the valve, and it will either go from left to right or right to left. So with this R parameter, so plus minus 1, we can basically control the flow direction. And we are interested in the mass flux, so the flux of the normal component through the boundary here at the inlet. That was the main idea. Okay, and we wanted to do this with our nice method. So Christoph already mentioned that we have this high order diff-free flag that you can set or unset. There are more comments in this thing here because I'm using it, but I will skip this here for now. You can read through that to get the method a little bit simpler. So this is something that we have already known. So basically what we now have again is our HDiff method, so Vt, V hat, and our pressure space. I haven't seen that, I'm not sure where this is coming from. Okay, and here just a very short comment on this IMAX splitting scheme. As already mentioned, you can find more information here in the docu. Basically, the main idea is we want to do Stokes plus time implicitly, so this is this M star thing here. And we want to have the convection explicitly, because this is the nonlinear part, and we want to do a fast assembling routine here and put it on the right-hand side, and just factorize this matrix here once, and we hope that we can get a very fast method here by that. Okay, so this is the left part, so this is this implicit part. Okay, I really don't have a lot of time. We have the convection here. Maybe a short comment here regarding the convection. So, no worries. Basically, I will just, so there's a lot of introduction or more comments here as well. So, what is new also in NGSolve, what you can do now for this HDiff space as well, is that you have a nonlinear matrix-free PDB operation. So the idea is that here, in this convection, you can actually reformulate it in a geometry-free implementation, and you can actually then do the application of this convection bilinear form, so this right-hand side, on your graphics card, and this is much faster. Joachim hacked in here last week. So yeah, this is. Oops. Better. Yeah. So. Oh, okay. Yeah, this is super stupid. Good. So, again, as mentioned, there are a lot of more additional comments, but since we have only 6 more minutes and everyone is already close to a breakdown, basically what we are doing here now is we do all these solving routines, we do this very fast application, and maybe we go just to the results. This is now the flow that you see, maybe I zoom in a little bit, from the left to the right. So basically what you see here is now it goes down here, it goes up, and you see it somehow stops itself. So for example, if it goes back here, you see these oscillations here, and this vortice is building up. Okay, so this is the orientation from the left to the right side for about 30 seconds simulation time. And here you now see the flow profile from right to left. So you really see this nearly looks laminar, so it really can squeeze in through the valve from right to left very easily. Okay, and what we expect is now that also the flow rate is somehow different. And yeah, indeed, you see that the flow rate reduces here. Okay, and I think as a closing comment, you can do, I think the last one we will skip anyway, but you can do also an IMAX scheme or a Navier-Stokes implementation also in parallel. For this we use this Corrine splitting method. This is some kind of a projection method. You can do this, and it is also very well suited to be done with the HDiff space. But more comments on that here. So also the idea of Christoph and me was we put all we know into these slides, and a lot of the things we know. Of course, not everything. We have something to hide. Yeah, we do now this solve here. So we do this again MPI parallel. So this was the main idea here. It looks a little bit just like a box, but we have something hidden in here. So maybe you're maybe you're familiar with this object here. And yeah, so basically we do a Stokes initial solution, and we do then a flow. Yeah, so basically then you have the flow around your NGSolve logo. Okay, and maybe you want to spend a few minutes on the VTK just that it is possible. Then you have seen what microphone. Okay, now this takes already 5 minutes.
5 minutes. So yeah, so back in the day when there was no web GUI and a kind of constant support on fancy visualization features, and especially before when I was in Aachen and not using NGSolve, we worked a lot with VTK and kind of doing some numerical PDEs, putting the results in this VTK format and then visualizing with different tools. And that you can also do in NGSolve, so there's a VTK export. So if you have some data, you can also export this to VTK format. The advantage is typically if you have more complex visualization filter pipelines that you want to do. So you have some geometry, you want to cut the result, you want to compute isosurfaces, and then on the isosurface you want to compute the vector field or whatever. So if you have more complex things, then at least so far this is not directly doable with a web GUI, although we I think have very nice feature set already. And here's now a very short explanation of what you can how you can actually use that. So we use PyVista, so which is kind of a VTK compatible visualization library for Jupyter and Python. Obviously, otherwise, if you want to rather work with an external GUI, you might know ParaView. It's kind of the same logic. So PyVista also allows this type of pipelining, as you might know from ParaView. Okay, so you need this external tool. So if you want to do something like this, then yeah, you do need to execute what we've written down here. And okay, let's see how the NGSolve side of things is essentially what you can do. You compute something or you set something up, and you get a coefficient function. Yeah, so typically grid function is the coefficient function that you're most interested in. But okay, whatever your coefficient function is, or the set of coefficients that you're interested in, you can just kind of put this in a VTK output. So by the way, so the last one working on the VTK output is also here. So Tilman from Aachen. So he had to kind of modernize this to binary output. Even so, you essentially prescribe a list of coefficient functions that you want to put out. Could be vector valued, could be scalar valued. You put corresponding names that are used for identification later on. So VTK typically is low order. Yeah, so there are some high order flags, but let's say it's quite limited in storing high order information. So what you typically do as a poor man's solution for that is you add a subdivision on your underlying mesh. So essentially what you put out there is then a subdivided mesh. So you don't have to. So if you take a look at the mesh that you get from VTK output later on, it will be much finer than you might have in your NGSolve just for visualization of higher order functions. Okay, so yeah, so actually, okay, so, and then you can just essentially very easily read in VTK information. So this is an output file that you might have wrote now here from this NGSolve call. It gives you a data file that you can just read in then, and then you can plot. Okay, so now there's a problem essentially different than the web GUI. This PyVista does not generate inlined HTML. It rather does this in a different, let's say, temporary environment, so that it's not rendered here in the right version. However, how it would look like is you can see essentially here in this type of thing. So you would get also kind of like the web GUI, such an applet if you run this interactively, and you would get kind of can visualize functions. So at this point, not how do you get back? Not more fancy than web GUI. Yeah? Okay. Mac and I are not that used to each other. So okay, and now you can essentially do lots of different things. And perhaps the most interesting part to mention is, of course, that you can now set up things like a plot, so visualization like our scene and before. Now you can do several things one after another. So you can introduce orthogonal slices through your mesh, visualize some quantities on that. You can also add streamlines, and all put this into one in one plot if you're interested. and let's say the most. Sorry, what? It's hard to read. Yeah, I think the concrete syntax is perhaps also not super interesting. I also would need to look it up. But you can then essentially run this and combine, for example, multiple meshes or filters in just one plot. Now, this is actually not the example where you have the full complexity, but this is now the geometry that Philip also showed before, and essentially see now streamlines around this orthogonal cuts or whatever, so you can essentially compose the visualization that you want to have. Yeah, I'm too weak for Mac, so that's difficult. I think there's a last one that I didn't show. Yeah, this is the one where you can actually also have plots like different fields next to each other. Here you see I've applied a few filters just to play around and have a second plot of something else there. Okay, so just in a short, you can also use this type of tools using VTK and filters, which might be interesting for some applications. Yes. Yes, that's what I said about the subdivision. I think VTK does not have at least not a very nice higher order. Recently, okay, then, okay. Then, but I didn't care too much about this so far, so I mean, yeah, okay.
What are you visualizing it? Because if you're an opening with quite a few, it's still going to do.
Yes.
Your standard visualization.
Now you have Chrome and all the other tool sets, so it's one of their web pages they mentioned format.
Okay. But high order, just use the web UI. Sure.
Are there formats available, such as DAT or saving this data?
So far, nothing that we support, I guess. I don't know if there's something that you developed on the site. I don't know. Other export formats for the data. If we have others, then VTK. And then you export to Patsy and from there to HF5 or what? Okay, cool.
Does it support higher order?
Sorry?
Does it support higher order?
We support higher order, yeah.
Which is HDF5 from NGSolve to Patsy?
Yes, because we did it for Fire, but for us, Fire wouldn't be able to use higher order matches.
And you have curved elements in Firetrack also?
Sorry?
You have curved elements in Firetrack?
Now, yes, but if you have the matching then yes.
Okay.
Yeah, that's it.
Okay, super. Okay.
What solver did you use for your Navier-Stokes simulation?
Which one? Or which of the both examples?
The one that you showed of the plane and if you're running the cluster, or also the second one, Stokes?
The plane
The
was.
plane was Stokes, sorry.
Yeah.
The second one, the one of the 5.
We used the Corinne splitting method, so we used GLG for the pressure poisson, and
You use geometric right multi-base for the pressure block?
for the Poisson problem in there.
Okay.
Yes, exactly.
Okay, and then
And something similar as before for the other one. Probably I show you. It's discussed in detail, but maybe I can
we had a good iteration, like
Yeah,
stable iteration with respect to the
Good. Okay. So thank you.